You have almost proved this in your homework already, I think, or you will soon. The proof is actually really simple. So what does it mean for f to have a 0? F to have a 0 of order n, what's that look like? F of z would be equal to what? Like z minus, zj, right? To the nj power times what? Times like h of z, where h of zj is not equal to 0, right? That would be what the factor theorem for a holomorphic function says, right? We can factor out from the power series a z minus j to the power nj power if it's a 0 of order nj, and then likewise, what does f of z look like if it's a, if p sub k is a 0? You have what? Something like k of z, right? Divided by z minus, let's say, p sub k to the power what? Well, to the power m sub k, yeah? And again, you've got that the k of the in this case pk is not equal to 0, right? And of course, the h and the k, they're both holomorphic at the points in question. Yeah. So, and then what happens when you look at f prime over f for these? So let me just suppose f of z is equal to, like z minus, I don't know, let me say a to the m power, and then b of z. All right. What is f prime? What's f of z, f prime of z over f of z equal to in this context? You got yourself a what? You got yourself a m z minus a to the m minus 1 b of z plus z minus a to the m b prime of z, right? Divided by what? Divided by z minus a to the m time, well, that's it. No, it's not. I'm a dummy. B of z. So how does that simplify? I suppose that simplifies as m over z minus a, right? From these two. And then what's the second term? Yeah, b prime of z over b of z. Right. So what's the residue then? What's the residue of f prime of z over f of z at a? It's just m, right? So what's this mean?
Value of that integral was 2 pi I m.
Right. Exactly. So notice that I did this calculation. I didn't tell you if m was what? Positive or negative, right? If and you notice the funny thing is, whether m is positive or negative, the division still works out to the reciprocal like this, whether it's a pole or not. You still end up with the multiplicity here as your residue. However, it's only the multiplicity when it's a 0, right? When it's a pole, what would we actually this wouldn't be the m sub k here, right? Because to get this expression to look like that, I have to flip that downstairs. So the m sub k would be minus this m. And so literally you just apply Cauchy's residue theorem to this. And this is how the residues calculate, which gives us that. That's the proof. Yeah. So, let's see here. All right. I need to erase something. I guess I'm going to erase this example. Now, I mean, you notice that if the boundary of D, if you replace boundary of D with, like, if you just wanted to, you could wrap the boundary of D k-fold times, right? And that would just multiply multiply this result by k. I don't know why you'd want to do that, but if you wanted to, you could. Well, here we go. So at this point, I point out that I'm essentially back to this at this point in the discussion. So the integral along a closed curve of the derivative of the natural log of the modulus of f of z, all right, is equal to, like, the natural log of the modulus of f of b minus the natural log of the modulus of f of a. So here, I'm not thinking of gamma as closed for the moment. Suppose gamma goes from a over here to b, all right? Then that would be that integral. So of course, if it's a loop, that integrates to 0, right? If it's a closed curve. And so what this tells you then is that the integral of the differential of the argument of f of z is equal to arg of f of gamma of b minus arg of f of gamma of a. And for a piecewise smooth curve, we simply repeat this calculation along each piece and obtain the net change in the argument as we trace out the curve. That's argument principle 2, which I should write down, if I can find my working marker. So argument principle 2 says that the the integral around the boundary of D of the differential of the argument of f of z is equal to 2 pi times the number of zeros inside the region minus the number of poles, both counting multiplicity. What it is?
I don't understand why.
So on the one hand, we have argument principle 1, which calculates that this integral is straight up. Notice the division by 2 pi, right? You have what happened with the I? Oh, well, there's an I here, right? See this I? That cancels with this I. And then we multiply basically, so all of this, right? This is equal to the number of zeros minus the number of poles, right? That's argument principle 1, right? So since this I and that I cancel, you just give 2 pi times the number of zeros minus the number of poles is the integral of the differential of the argument of f of z. This is actually very interesting because this means that if you can track how the angle of the image of your function changes along the boundary of a region, that tells you how many zeros and how many poles are inside it. Well, the difference, right? So in particular, if you knew that your function was, say, holomorphic, it didn't have any singularities inside a region, if you can study the change in the angle around the region, that tells you the number of zeros. Let me show you a simple example of this. What are we, example 4? How about this, like f of z equals z to the 4th plus 1. And like, let's look at the circle of radius 2. You guys know that how many zeros are inside the circle of radius 2?
Where's the circle?
Radius 2. Oh, where is the circle? That's a good question. 0 by default. Come on, man. Fair enough. Fair enough. You got me. I just assume everyone puts their circles at 0, but for you. What? You put yours at 136?
Not at 136.
Yeah. Not at 136.
136.
Oh, yes, 136. Yes. So, all right, so here we have z equals to 2 e to the it, right? So so that's my quote-unquote gamma of t. So what is f of gamma of t here? You've got 2 e to the it raised to the 4th power plus 1, right? That's 1 plus 16 e to the 4it. Notice that this argument principle says to understand how many zeros that function has, I need to look at the change in the angle of the image of the curve under the function. Where's the image of the curve under the function? Can you guys think about how to graph this? What's that look like? Because last time I tried to lecture this material, it blew my mind. I was watching a video, seeing what I did a few years ago. I was like, oh, I got stuck on this. But it's actually really simple. It starts at 17, right? So this is a circle centered where? Centered at 1, right? This is a circle centered at 1 with radius what? 16. So it's like over here or something, right? It starts there. And here we go. T equal to what here at that time? My first loop. How many times did it go to loop around once? No. 4it.
1/4 pi?
To get this to 2 pi, what do I need? Did you say 1/4 pi?
1/2 pi.
Pi over 2.
Pi over 2. Yeah, this is t equals pi over 2 for my first loop. And then my second loop, there we've now reached t equals to pi, right? And then again and again. I'm out of colors, more or less. So that finally we got to t equals 2 pi, which of course is I'm talking about, and t equals, so the boundary here, right, of the circle, the disk of radius 2, right? The boundary doesn't get covered 4 times. The boundary is covered once. So the parameterization goes from 0 to 2 pi. But the image of the parameterization does not go once. It does what? It goes 1, 2, 3, 4 times around the circle of radius 16 centered at 1. What's the change in angle for the image curve?
2 pi.
No.
8 pi.
8 pi. Because the change in angle, it's not a displacement. It's like distance traveled versus displacement.
Oh.
Think of distance traveled. So it's the net change in the angle, but it depends where you went to. So anyway, 8 pi, which then says what? Argument principle number 2. So we should expect 8 pi, right? So we got 2 pi n sub 0 is equal to 8 pi. Therefore, n sub 0 equals to 4. Of course, we know n sub 0 is equal to 4 because we can factor that thing. We know that the zeros are the 4th roots of -1 anyway. This might not seem like a very helpful thing, but I will show you next class that this allows us to prove the existence of zeros of things we don't even want to start to try to factor. So it's actually a calculationally very sophisticated, powerful tool, ultimately leading to Roche's theorem, which gives by far the easiest proof of the fundamental theorem of algebra that you'll see in this course. So that's next class. So I would say if you want to, you might wait on the Roche theorem problems. You can go ahead and do them if you want, but I'm not there yet. I'll get there next class. I'm sorry. I would have got there this class, but another 15 minutes.